have their office hours slightly longer because I know most of you wait for questions until the last week. So far it's been going pretty smoothly. Yeah. Okay, so I think there was just feedback on Canvas posted about the proposals. Most of them were great. There weren't a lot of issues with them. A few of you may have gotten more detailed comments. Again, at any point and you have questions about what to do or how to make progress on something, feel free to come talk to me before, after class, in office hours, or just send me an email. You know, I try and respond to these fairly quickly. And usually that helps your proposal a lot to get, if you get more feedback. Okay. And then homework 1, unfortunately, has not been graded yet. However, the grade should be posted probably later tonight. The TA who was in charge of these had the bad flu last week, so it kind of set the grading of these so behind. Okay, so today we're going to talk about assignment-based clustering, but I want to start by just listing some numbers on the first homework. So there are these questions, question 1D and 2D, where I ask you to run these. Question 1D was on the birthday paradox, and question 2D was on coupon collectors. And these are the largest setting I asked you to run at, and I asked the TA to collect some statistics on how long it took people to run these. And so you can see the coupon collectors problem, and this is just the largest setting. This is coupon collectors. It ranged from half of a second at the largest scale all the way up to about 4 hours. Okay, with the mean around 5 minutes. I think that's a pretty reasonable amount of time to have to run something on average. And for the first one was birthday paradox. This was the birthday paradox. This one was the coupon collectors. Coupon collectors took a little bit longer. Someone got down to 18 seconds. That's the largest scale with the average of about an hour, and the longest it took someone was 22 hours. Okay, so you know I think this is reasonable. Everyone finished. So that was good. But it points to there's a kind of a difference in how you implement these these answers. So if people have questions, you know, I think if anyone, and I think these numbers, I think with so Stone, I think you posted about Numba, and I think this really reduced a lot of the run times. So how many people use Numba to speed up their stuff? Okay. So there's this Numba that was posted on Canvas. That's something that precompiles Python, and it dropped the runtime was a factor 100 or something like that. Yeah. So that probably accounts for for some part of this.
You do have to write your code a little bit differently though. It only takes like primitive data structures. Like you have to use sets instead of hash map or dictionaries. So.
Oh, okay. Okay, yeah, so, you know, even though you can't just magically plug in and get all the speed up, but it kind of points to the thing that you should, you know, if you think about carefully implementing these things, you can squeeze a lot more, like, you can squeeze a lot more efficiency out of these. So it's not something that should be ignored. This difference of 18 seconds to 22 hours is pretty large. And this will come up throughout the rest of your career. Okay, so this isn't so much an algorithms class. I'm not going to dwell on this, but it's just a point to keep in mind. All right. Okay. So the topic of today is going to be find my notes. Is going to be assignment-based clustering. Okay, and so this is covering things like, and so On Monday, we talked about clustering in general and this hierarchical agglomerative clustering, which is this very general modeling tool, but the algorithms were weren't too efficient. So now we're gonna, but it was very general, the type of clusters that we can imagine. In the assignment-based clusterings, these have a much more formal model. It says, this is exactly what I want to optimize in clustering, and then comes up with some pretty clever algorithms and simple algorithms that are efficient that can optimize those specific formulations. Okay, and so the most famous of these, right, is probably Kmeans, right? So who's heard of the Kmeans clustering problem before? Who's never heard of this before? Okay, so a few of you haven't heard of this. Okay, we're going to talk about that, but also some other things as well. So, for instance, who's heard of the K-center clustering problem? Okay, great. Only a few of you. And who's heard of K-means plus? Okay, so if you run K-means, you should also run K-means plus, and arguably, right, you should kind of use these together. This is the right way of doing it in most cases. And I would argue that this K-center problem and the algorithm that comes with it, the Gonzales algorithm, is as fundamental as Lloyd's algorithm for K-means. It's as simple, kind of, it has different trade-offs, but it's even simpler than Lloyd's algorithm. So we'll hopefully, even if you've seen some of this before, you'll get a lot of new stuff out of it as well. But we're going to try and cover all of this today, maybe including mixture of Gaussians, depending on how things go. Okay, and this will be an example of soft, essentially a soft clustering version of K-means with some extra information. All right. Okay, so in order to define this, again, we're going to start with an input x, and for this lecture, I'm going to decide that this is a set that's in RD. So these are going to be d-dimensional vectors. I don't necessarily need this in general. You can think of it as an object, right? So this is x1, x2, up to xn. Are there questions on this? Was someone asking a question? All right, thanks. If you have a question, please ask it so the whole class can hear. Great. And then you also have some distance, which is going to be defined from RD across RD to R. And so for some of these, I'm going to require that the distance is between x1 and x2 is going to have to be is going to have to be the Euclidean distance. This won't always be the case, and I'll try and distinguish between these. But for some, so it's enough for most of the examples I'll give examples in 2 dimensions, and we'll actually use the Euclidean distance. Some of them, it just has to be a metric. Sometimes the distance has to be defined on the domain that x lives in, but usually this will be RD. And sometimes it just needs to be defined in between the objects in the set X. Again, so this was similar to in the setting we had on Monday. But we'll have some specific restrictions to where it has to be the Euclidean case or it has to be a metric in the lecture today. Okay, and then to describe this, I'm going to so in order to describe this, I want to use a shorthand notation of a function. Well, okay, let's start with something else. I'm going to start by saying I'm going to have the output. The output is going to be defined in 2 parts. The output is going to have a set of centers, and I'll call these C1, C2, up to C K, and there's a whole set C. So this is an uppercase C, and those centers are lowercase c's. These will also be points in RD. And so I'm going to define this mapping function. Which is going to go from RD to an element in the set C. And in particular, this is going to be equal to the argmin center in the set C of a point x, of the distance from x minus C. So this is going to take in a point x and map to the closest of the centers. Right? So if I draw a picture here of the input data, right? This is x, and I'm going to have three centers, C1, C2, and C3. Then there's going to be some function where anything in this range over here, is all going to map to C3. So everything in this green region, the closest point is going to be C3. Everything in this light blue region over here maps to C2, and everything else maps to C1. Right? So it maps every data point onto its closest onto its closest center. And essentially, that means every data point then has a cost. Right? So I'm going to have a cost from every data point here. Say this is x1. It maps onto C1, and there's some distance. This distance from C1 to x1 is essentially some cost associated with this one point. Okay, so I want everything to be mapped to the closest center, so I have the smallest possible cost of it. Okay, and so this is assignment-based clustering because I'm assigning all the data points onto the centers. Okay, my output is only describing these centers, and then this mapping function can be described implicitly. So I don't need to kind of return all the data sets and the whole clustering again. I just need to return these centers, which are representative of each of the clusters. So the output is somehow a much kind of more compact summary of what's going on. I can annotate this with how many points and other stuff as well, but for now we'll just return these centers. Yeah?
What's underneath argmin?
Argmin, one lowercase c in uppercase c. So this is a lowercase c in the set of centers. So this is, I could call this Ci, right? One of the centers in the set of all the centers I have. Okay, and my goal is to choose these centers so that it represents the data as good as possible. Okay, now what does as good as possible mean? There are a few different formulations of this. So the Kmeans formulation is the most common, and that's where there's some cost, we'll say cost 2 of x and the set of centers C is going to be equal to the sum over all of the data points in x from the distance from x to its closest center of x squared. Okay, so I'm summing over all of the data points. Each data point gets a score, and I'm measuring its squared distance. Its squared distance from the data point to its closest center. Right, so it always maps to the closest center because that's its implicit representation. Okay, I could actually encode a specific center it's mapped to and then do that, but it's always going to be the closest one. That's the one I want to use. Right, so I want to pick a set of centers so that this mapping on average the squared distance is as small as possible. As the squared distance here, there's the K. There's the K median so formulation, which is, I'll call cost 1 of x and c, which is the same thing except d of x. So this is the same, but I don't square this. It's the same thing, but without the square. Okay? So the k-median does not have the square. The big difference here is the square term. It turns out this one will be a lot easier to work with than this one, and that's the main reason why we have the square term, because it'll be easier to do, not because this is a better formulation. Yeah. Okay, great. Yep.
Does this implicitly mean that the distance d could have negative values?
No, a distance should always be, okay, I've seen some weird variants of this where a distance can be negative. But in general, distances are always greater than 0, right? I could be using a weird distance where it could be negative, and that's fine. Like the Lloyd's algorithm we'll talk about for Kmeans, this has to be Euclidean distance, which is always positive. The K-median formulation, you could probably use a different distance here, like some power distance that can have some negative aspects to it, and then it could be negative and it could still work, I think. Yeah.
So when you say that the K-means formulation is easier, is it because you don't have to take the square root of it?
So we'll see why. We'll see why. There'll be Lloyd's algorithm, which we'll see. Who's heard of Lloyd's algorithm? People took my class last fall. Okay. So Lloyd's algorithm magically works really well with where you do an averaging step, and that corresponds with the K-means formulation, and that's why it's easier. So we'll see that in 15 minutes.
What is K?
K is the number of clusters. Yeah, so let me add that to input. So you get 3 things: the data set, the distance, and K equals number of. Okay, and so usually we'll discuss this as that's given as input, but that's like the eternal question about clustering. How do you choose K? We'll discuss this later on in the lecture, but there's some quasi answers I can give you, but no definitive perfect answers.
Are these two formulas, are they in the same metric?
Yeah, so I mean you can use any distance function in these formulas, right? To use Lloyd's algorithm, you need this to be the Euclidean distance. Okay, but I could plug in a different distance function that does not need to be a metric into these formulations, and then I can try and solve it. Right? But generally, we want it to be a metric. Generally, we want this one to be Euclidean. This one, if it's not Euclidean, it's even hard to work with. I'm going to mention something called K, K-medioid. Let me write this down here. K-medioid. This is the same, but C needs to be a subset of X. So the centers need to be in the data set. This K-medioid, so it's median and medioid. I don't know where these names came from, but so this one is easier to work with in any distance function because I can kind of search for the centers over the data set. I don't need to worry about it being in some space of objects, like in all of RD, or maybe I'm clustering over a set of curves of like trajectories of people. How do I come up with an object which is not one of my data points? That becomes a much stranger thing to think about. So if you say K-medioid, then I don't need to worry about this. I just need to formulate a distance, have a data set, and have a set of these clusters, and then I can deal with this. Was there another question back there?
Yeah, I was going to get back to the idea of the Euclidean distance. If you don't use an L2 norm, would you have a different power for your K-means formulation? Like if you used an N norm, would that be D to the power of N?
So I mean, it's just a formulation, right? So I can put any distance function in there. The distance function could be the squared Euclidean distance. That's a distance function, it's not a metric, right? And then if I say K-means with that distance function, it means I'm taking that distance and I'm squaring it. That would be the the Euclidean distance to the 4th power, right? Typically, you use this with Euclidean because Lloyd's algorithm, which we'll talk about, works out really nicely. If you're not using this special Euclidean setting, although which is a very common setting, then you'd probably use the K-median. The squared is just something that makes this work out. Or you'd use the K-medioid because then I don't need to worry about being in some understanding the space of objects. I can just search among my data points. And then there's one more common formulation, right? So there are K-means, K-median, and then there's the K-center. And the K-center formulation is cost infinity, right? Which is equal to, just like the L infinity is the max over x and x of the distance from x to phi of c of x. All right, so here I'm trying to minimize the furthest distance from any data point onto its center. So I want every data point to be not too far. Right, so I will only care about the worst distance. So these are kind of averaging, and I could divide by 1 over n, and I can average distance here. Here I only care about the largest distance. Okay? And so these are the 3 or 4 with K-medioid most common formulations of this assignment-based clustering. Right? And so now I can say, okay, I have a cost function. I want to find this set of centers which minimizes this cost function. Okay. It turns out in general, like these sorts of problems are NP hard to solve exactly in most cases. In fact, with Euclidean distance, with the K-median formulation, you may not even be able to express the right answer algebraically. Right? It may not be the centers which optimize it may not be so rational numbers, right? So I may not even be able to write down kind of a formula how to calculate them either. So I'm not going to solve these exactly. We're going to describe some algorithms which, in some cases for K-center, give a nice approximation to the optimal algorithm, or in the K-means, something that generally works very well in practice. And maybe you can say some stuff about how well it works under some cases, but there are weird cases where it doesn't work. Okay, so so we have a cost function now, but that doesn't mean we can kind of say we're going to exactly find the optimum for these cost functions, unfortunately. Okay. Any more questions about this set of formulations? Okay, so this is a more clean setting, right? We've kind of restricted the problem to this thing where all the points map to the closest center, and that's how you define the clusterings. So it always looks like kind of this division of the space into these nice regions. So it kind of restricts the type of clusterings I get. For instance, if we go back to that 2 moons example with single link clustering, I can't find those 2 different moons under this formulation. Okay, but under this formulation, there are a lot of kind of nice stuff that works, and it's nice and clean. And the output can just be described by the set of centers. So it's a very simple representation. Okay, good. Okay, so the first thing we'll talk about is the Gonzalez algorithm for K-center clustering. Okay, so K-center clustering is just a formulation. There are many ways you can try and solve it. The Gonzalez algorithm is kind of the simplest and the thing that basically everyone uses. Okay? And so this one, just a few notes, is NP hard to solve within a factor of 2 of the optimum. Okay, so if there's a clustering formulation, a set of clusters which minimizes the cost, there are some data sets that you can give in so in general metric spaces where finding the right solution within a factor 2 of that optimum is less than a factor 2 is NP hard to do. You can beat this. You can get within like factor of like 1.8 or something if you restrict to the 2 dimensions and the Euclidean distance, but it's essentially still hard to get the exact hard to get the exact answer. So question.
What is NP hard?
Okay, so NP hard is so is something you would learn about in like an algorithms class and a computer science class. It's a way of measuring the complexity of certain problems you're trying to solve, and so it's believed that problems that are classified as are proven to be NP hard would take exponential runtime in the size of the input. Okay, it means something slightly different than this. It means that if you had this magical parallel machine that could solve all instances at once, then you could solve it in a way that's efficient, and you can verify if you have the right solution. But in general, if something is NP hard, you expect, in order to get the exact solution or a 1.5 approximation, I would need to spend exponential time. Like I would need to try, I would need to do something like try all possible subsets of points in order to define my clusters, and for each one of those, find the optimal point, right? And that would take exponential time to try all of these. Okay, so it's going to be hard to do better than a 2 approximation, or it would take way too long. Okay. Right. So the Gonzales algorithm, however, is going to give a 2 approximation to the optimal solution and works in any metric. As long as the distance I'm using is a metric, then it's going to give a 2 approximation. Often it's going to work better than a 2 approximation. That's kind of a worst case thing that you can easily show, and often it does better than this. But it's never going to do worse than a factor 2 of the optimum. And you provably, in general, you can't do better than this. Okay, it's also a very, very simple algorithm. Okay, so let's see the algorithm here. Let me just write down the algorithm. So the algorithm is going to build the centers just one center at a time, and I'm going to build k centers, and so I'm going to run this for k steps. Okay, so for step 1 in the algorithm, I'm going to choose center C1 as an element of the set X, so arbitrarily. So I can pick any center, any point as the first center, and then I'm going to let this set C1 is going to be a set with only one element in it, and it's just going to be that center. So this is an uppercase set of centers. I'm going to define a set of centers, and I'm start with a set of size 1. Okay, so I'll use this for, I'll label it 1, so for notation purposes. In general, I'm going to have set Ci, which is going to be the center C1, C2, up to Ci. Okay, and I'll stop when I get up to Ck. Then I'll have all the centers. Okay? So then the algorithm just then repeats for I equals 2 to k. I'm going to do the following. I'm going to set Ci, so that's the ith center. It's going to be the arg max over all the x in my data set of the distance from x to phi of ci minus 1 of x. Okay, and this is the whole algorithm. Okay, so every step, let's look at what this means. This is, remember, from every data point, I'm looking at the distance to the closest center. This is the closest center in the set of centers I've found so far of each data point x. And I'm going to find the one that has the largest cost, and I'm going to and I don't want ones with large costs, so how do I reduce the cost? I'm going to take that one and make it a center, and then its distance to the set ci, which would then include itself. So then it'd be the distance here would be 0. Right? So this distance goes to 0. It's a metric, right? So the distance to itself is always 0, and this is no longer what is the maximum. So I've reduced the maximum cost in this way. I found the one with the largest cost. I want to reduce the maximum of all the costs, so I take that one and I add it to my set of centers. That one goes down to 0. And I just repeat this until I have k centers, and I stop. Okay, and that's the whole algorithm, right? So it's probably the simplest possible algorithm you could do for clustering. Yeah.
I wonder why we need the capital CI.
Okay, so I'm always measuring from the set of centers I have so far. Okay, so let me kind of walk through kind of a simple example here and just see how this works. Right, so I'm going to have these. Okay, so this is going to be my data set, all these small little points down here. Right, and so now I'm going to pick one point. Let's say I pick this point as my first center. This is going to be C1. And now, I get a score by mapping everything onto this, right? So the set of centers doesn't matter so much so far. And I'm going to pick the furthest point from this point here. Right, so let's say the furthest point is down here. So this will be C2. Okay? Now what's going to happen is that this is going to kind of divide my point set in half. Right? And now all of these points are going to be closer to C1. All of these points are going to be closer to C2. Right? So now I don't want to just find the closest point from C1, but the closest point where its assignment is to C1. It turns out this point is the furthest from C1, and all these points, it's even further to go to C2 than it is to C1, but I only want to measure the distance to C1. Right? So then, in the next step, change color so you can see it. I pick this as C3, and what's going to happen is now my notion of the mapping is going to change. It's something like this. Right? So I'm still going to get this split here. But now all these points are assigned to C3, these are assigned to C1, and these to C2. Right? And we're going to find the next furthest point here. Let's say the next furthest point might be over here. This would be C4. Can you see that color? Yes or no? No? Okay, let me try this right here. So I'm going to pick this one as C4 in green. You can see that. Okay, so this is now C4. And so notice this is the furthest point from C3, but that does not what matters, right? It's closer to C1, so this was its score. And so that's why these sets matter, right? So if I keep running this, just kind of see what this happens, right? I'm going to add in these other sort of dividing lines here. This stays the same. Then probably after that, I'm going to get, I'm going to pick probably one of these points here. This will be C5. Right, so now it starts to do something a bit more interesting. it's dividing up the space like this. Right, so I'm going to get some division here. All of these points in this cluster map to C5, C2, C4, C1, and C3. And then maybe I run in another step and I split this into 2 clusters. Right, but that would be the next thing it does. So it's kind of, if you started and said there were 5 clusters, 1, 2, 3, 4, 5, it found those clusters. It worked. Right, so this is a very simple algorithm, and if the data set is like really well clusterable, just this simple algorithm works pretty well. Right, and I can implement this pretty quickly. Let me just add a note on how you would implement this. Just an idea of implementation, I would store in an array from 1 to up to n each of the data points. So this stores xn, all the data points in some sort of array, and then don't touch that. All the data is stored and is fixed, right? So this is the data array, and then you have an assignment array, where you initially assign everything to cluster 1, right? And then as you go through it, I update some of these to cluster 2 when I've assigned to cluster 2. Right? Once I make a cluster 3, I can say, okay, this one was now assigned to cluster 3. I just have to store which cluster it's assigned with, and I keep a separate array over here that has C1, C2, up to CK, and I build those as I go. So then if I want the distance, I know it's mapped to the index into here, and I can just recompute the distance if I want the distance. Or I can have another array that stores all the distances, and then I can keep track of the max. So I can update this pretty quickly. You don't necessarily need to build kind of an object-oriented data structure around here. Yeah.
When you say choose center arbitrarily, what do you mean exactly?
You want to pick the first one arbitrarily?
Yes.
I can, I have these stored in an array. I can say that this one is C1, the first one in the array. That works fine. It's guaranteed to give a 2 approximation to the optimal solution, no matter where I start. After that, it's deterministic. So the only choice I have is which one I choose first. And it doesn't matter so much which one you choose first.
So where in the algorithm, where are you assigning the clusters for every data point?
It's kind of implicit, right? And that's always implicit that every time I choose a new center, I can go through this list and calculate the distance from x1 to this new center. Yeah. And if I have stored the old, I know it was mapped to center C1 before, so I know the distance. If it's less than that distance, then I assign it to the new center. I don't have to recompute the distance to all the centers every step. So I go through it and I reassign them, and then I calculate. While I do that, I keep track of what had the maximum score, and then the next time around, I just said, well, I knew which one was the maximum. I kept track of that, and that was my new center. So in the notes, I kind of give some pseudocode with a lot more detail on how to do this, but it's super simple. You all implement it in your homework, and you'll get to experience it yourself. So. But it's a good thing to just do because it's not too hard to do. Okay, so any questions on this? You can use this in any metric space. The set of centers in the formulation does not need to be from the set of objects, but this gives you a solution where they are the set of objects. I could do some stuff and try and optimize. One downside of this is the centers tend to be on the boundary. They tend to be as extreme as possible. They're all the way kind of out as far as they can be. So you might try and recenter these among its clusters, do something to try and minimize this afterwards. You can do that, or you can do what we'll describe next, which is Lloyd's algorithm. Okay? Okay, so there are some weird artifacts that can sometimes come out of this, but it'll still work pretty well in general, as long as your data is well clustered. Okay, now let's talk about Lloyd's algorithm for K-means. So the K-means, again, is a formulation, and there are other algorithms for it. Lloyd's algorithm does not have any guarantees by itself. There are other algorithms that have guarantees of near optimalities from approximation factors. Lloyd's does not have those guarantees, but it's what people tend to use. In some cases, it works well. If your data is well clusterable, in general, it works well. And I'll give you some pointers on how to use this one. Okay, so again, this is the K-means formulation. So it's minimizing the sum of the square distances, and we'll assume that the data is Euclidean. We'll assume that D equals Euclidean, and X is a subset of our D. So this is, let me say the distance is Euclidean. Okay. Okay, and so to describe this, let me just start with the pseudocode here. So I'm going to start by choosing K centers C, and typically as a subset of S. And this can again be arbitrarily. Okay, and I'll come back and comment on this again. Right, but again, I'm just going to start with some centers. Now I'm not starting with one, I'm starting with the whole set. Right, I'm gonna not just choose them one at a time, I'm gonna kind of try and optimize them, choose them all together. And then I'm gonna go into a loop, and I'm gonna repeat this loop, these two steps. Okay, so for all, so here I'm going to explicitly write down this, this finding this nearest neighbor. So I'm going to find this, and so I'm, let's say, set x to ci, which is equal to our, let's just say c of x, r min ci and c of x minus ci. Right, so at this point I'm going to write this down explicitly. I'm having a step here where I assign it to the closest center. Before, that was kind of implicit in the Gonzales algorithm. And then step B, so I'm going to say for all CI, so for all the centers, the first step loops over all the data points. This is going to loop over all the centers. I'm going to reset the center at this point. So I'm going to set the CI as going to be the average over the set of all points assigned to this center, such that phi of c of x equals xi. Okay, so this means the set of all data points, the x in big X, such that, this line means such that, the assignment of x, is equal to ci. Right, so that the assignment of x, the closest center is ci. So I'm going to take all the points that are assigned to center ci, and from that set, I'm going to reset ci to be the average of these points. Right, again, the average is, I'm going to call this set, let's call this set Si, is this, all the points which are assigned to center xi, and then the average, this ci, is going to be 1 over the size of ci, sum x and si x. Okay, so in one dimension, you all know how to take the average of just numbers. You can do this over vectors as well. The notion of averaging over vectors is done just by element-wise. Right, so these are all vectors because they're an RD, and I'm taking the average over these, and this is the new center. Okay, and then I'm going to repeat this until it's converged. Okay, and so what does it mean so it's converged? Well, I'm going to argue that at some point the set of centers is not going to change inside of one of these loops. That means that it's stopped. I can probably stop before then. I can probably run for 20 steps and it's fine. Or I could say that the change in the cost function has changed by a small enough amount that I can stop. I can stop at some point. Yeah.
Can the centers not be a point of the data set?
Yes. In this case, they do not need to be a point in the data set. And this is kind of what makes this efficient. I can set the new center as some average. And this is why it needs Euclidean distance, because the average I can just take the average and that makes sense over vectors. There's another, a little bit more detailed reason I'll say in a minute or two.
I was wondering, can we do anything like taking the distance of all the points with respect to a specific point and then just dividing the data based on that distance?
Okay, so what you're suggesting, right, is I have some data set, right, and then I take some representative point, and then I look at all these distances to this one point, right? What's going to happen is that I'm going to get the closest points in here, then the next closest points are inside of this region in here. You know, it's so this looks like a donut, right? Like with some sprinkles on top. And then the next closest points are in this region out here. And my clusters look like these kind of annuli, right? And so and in high dimensions, it gets even stranger. So this kind of works as like a space decomposition way to build something like a Katy tree in high dimensional metric spaces, where I pick a point, I look at half the points which are the closest, and then everything else further away. And this kind of works well there, but not so well for clustering, because I get this ring structure instead of kind of this spatial decomposition. If that makes sense.
Like initially we get this ring structure and then try to decompose the point within this.
Well, I could do something like that, but this Lloyd's algorithm works better. Okay. So there's some places where structures like this are useful, but they're in much more complicated and specific settings than what we'll talk about in this course. So if you're really interested, I can give you some pointers to some literature after class that deals with weird metric spaces that have some bounded doubling dimension, and you do want to use some structure like this to decompose the data. But this is, this isn't something that happens all the time. Okay, so let's go and talk a little bit more about this Lloyd's algorithm. And yeah.
I just wanted on step 2A at the very end, is that just the distance between the data X and C? That part that's kind of...
Yeah, so this is such that...
on 2A.
Such that 2A. Yes. So it's the standard definition of phi of C, right? So this is that's what's going on there. Yeah. So it's the same definition of phi of C I'm using throughout this lecture. Yeah, I just redefined it there. So it's if you're implementing it, you need to figure out whichever is the argument. And in this case, you need to just check the distance to all the k points. Yeah.
And sorry, what was that straight line on 2B?
This means so such that. So it's defining a set based on it needs to satisfy, it needs to be from this larger set, but it needs to satisfy this condition. So such that this condition is satisfied. So such that it's all the data points such that they are mapped to the ith center. That defines a set Si. And basically I'm just taking the Euclidean average of this set.
I'm just wondering if there's any way to like actually visualize it.
Yeah, okay, so let me, just like with the K-center, good. Well, let me go through an example of this again. Okay, so let's, right, so here's my data set. And because, again, we're in two-dimension Euclidean space, stuff will probably work out pretty nice. And so I'll start out with some set of centers, C1, C2, C3, and C4. Okay, so this is, if I look at the division that this creates initially, right, so these diagrams I keep drawing here are called the Voronoi diagram. This is the Voronoi diagram, and there's a lot of cool computational geometry involving these Voronoi diagrams. But okay, so I've divided up this space, and it's not quite right. Right? It does an okay job. It's got this center by itself, but this one seems to be split, and these two are combined somehow. So what happens is I'm going to reassign these centers, and I'm going to, this one gets moved a little bit more to its center. It's only averaging these points here, and so it perfectly centers itself on that cluster. This one, C3, gets moved a little bit over here. It's averaging all of these points, and so it moved a little bit in this direction. C4, well, it's moving, this isn't really helping so much, but C2 moves out here. C2 moves all the way out here because it's the average of this point, this set, and this set. Okay, so how has this helped? Well, let's redraw this Voronoi diagram here. Looks something like this. Okay. All right, so this has shifted. Now most of this cluster has moved on to C4, and C2 has a lot less of this. So I can run the next round of this. C1 is going to stay in the same spot here. C3 isn't moving as well, but C4 is now going to move up to here, and C2 is going to move here. It's still pulled a little bit from these couple guys, but it's mainly moved in place. Right? And now if I look at this assignment, right here, this is basically what this Voronoi diagram looks like. It keeps going. Then I have, in the next round, C2 will move here, and this will be right in the middle of this cluster like I like. C4 is almost in the right spot. It still has one little point down here, but it's pretty close. C3 moves pretty close to the answer, and C1 is still in the right spot. And then I'm going to move one more round here. What color? Oh, you guys can't see that. Okay, what? Let's try gray. Okay, so now, oh wait, I forgot to draw the Voronoi. Yeah, let's draw the Voronoi diagram of these, and it looks like now the Voronoi diagram has the right assignment. So I run this for one more step, and C3 moves to the middle here, C4 to the middle here, and those two stay in place. Okay, so in 5 rounds, I've perfectly found all the clusters, and I've probably actually found the optimal solution. Right? These are exactly at the middle of these clusters here. And it turns out that's the best you can right? So it kind of is iteratively readjusting in between the assignment of the points and the finding of the centers.
So why would we ever use the K-center clustering?
Well, this one is easier. The case center is a little bit easier. It works for any metric, right? So say I'm doing clustering over the Jacquard distance of documents. I cannot do this averaging step. I don't know what this averaging step is, so I don't know how to run this algorithm for if I'm using Jacquard distance, right? So if I'm using some non-traditional distance, then I can't use this beautiful kind of iterative process. Yeah.
Is the optimal solution only defined for a specific K, or is there a way where we can actually measure the solution the distance optimal? Not knowing.
Yeah, so the formulation is given a specific K. There's another question of how do you choose K, right? And might as well comment on this now. Choosing K, right? This is often a modeling choice. So part of it is that, I may want to divide, say I have a bunch of customers, I want to try and understand them into classes. If I have 1,000 different classes, that might be too much to really understand, right? So I don't want it to be too large. And if I choose 2, that may be too small, right? So there's some kind of common sense aspect of what is the right answer here. Sometimes someone tells you, find me 5 classes of customers. Your boss comes in and says, I think we have 5 types of customers, and I've got this chart I want to make, and it needs 5 different types of customers. Go find 5 classes for me. So he gives you, or she gives you K, right? So that can happen. But there's there's going to be this phenomenon where if I look at as K is increasing, and I look at the cost of XC, and let's say this is of the optimal C, right? So let's say I found the optimal set of the centers. What's going to happen as I increase K? What is this chart going to look like? Is it going to be increasing, decreasing?
When they have to go to 0 eventually?
Yeah, so eventually, when K is equal to N, it's going to be exactly 0. And when K equals 1, it's going to be essentially it's going to be the variance of the data. This is the variance of the data set X. Okay? And it's going to decrease. And it's always going to be decreasing. So it's probably going to look something like this. Okay? So your function is going to look like this. So as your K gets bigger, of course, the sum of squared errors is going to decrease. Right? So then if I keep making K bigger, I'm getting a better and better representation of the data. But at some point, it starts to kind of level off here. And so often what you want to do is kind of pick something here. It looks like the elbow, right? Right. Think of this like an arm here, or like this, and then there's an elbow on the arm, and you kind of want to pick where the elbow is, and this is the K star that you choose. Okay, because as I add more and more K, I'm not reducing the cost that much. What you're happening is you're along here. Maybe the answer is down here. Maybe it's here. I don't know. Somewhere in here is probably okay. But what's probably happening is there are clusters, and I'm splitting those well-defined clusters into 2 parts. Right? And so, sure, I get better accuracy, but I'm not really finding more structure. Whereas up here, these are points in different clusters, and I'm really kind of putting one center in each cluster in. So I drop the score a lot by just increasing K by 1. And so that's a good reason to increase K. If your data kind of looks like this, okay, so let's say the data is nice and 2D and it looks like this, how many clusters do you think I should pick? Or what do you think this chart will look like? if the data looks like this over here, if this is the data, it's probably going to kind of look like this. I'm going to get a pretty shallow curve. It's still going to be decreasing, but it's not going to have a sharp decline and then a leveling off. And probably in this case, there's maybe one cluster I should pick. I mean, there's not really clustering going on. A lot of data doesn't have, it's not clusterable, right? This is not clusterable, so I should choose one cluster, right? There's not really a sense of breaking it up. Maybe I want to say, okay, there's some decomposition I can do going on here. What's more common is that there's some region here where this region is very dense. And then there are some outliers kind of coming out in this way. And then again, there's no really good clustering here. But your data might look like that. You can kind of tell if it's good, well clusterable, if there's a sharp drop and then it levels off. This is what I would say is well clusterable, when it looks like this sharp drop here. And then that also kind of tells you how to choose K. Now, what is the right answer for K? Sometimes you can plot it and look at it, but usually you want to do this because you can't plot it and look at it and draw circles around stuff, right? So then you kind of have to look at this and use this plot to try and help you. So you run the algorithm for lots of different values of K, and then you kind of use this to kind of tell you what to do. Yeah.
What about the plot for example, cost 1 or cost infinity?
It's going to have a similar sort of effect. It doesn't matter so much what the cost function is here. There's something we'll see later in the course called modularity, which can be used for graph clustering in some ways that kind of gets around this choosing K issue, but there's some hidden parameter in there which is serving the purpose of K. In general, you always have some sort of K parameter like this, and you kind of need to do something like this to choose it. Okay, let me go back and say, I want to say one more thing about Lloyd's algorithm, and then I want to talk about step 1. Okay, so Lloyd's algorithm has the property. Well, okay, first I've got this loop here, right? This loop, I say repeat until it converged. Could this ever not converge? Could this ever get stuck in like some sort of infinite loop? No, yes, no. Who thinks it can get stuck in an infinite loop under some weird cases? And who thinks it can't? Okay, and who didn't answer? Okay, let's try this again. We'll do one more vote. Who thinks it can get stuck in infinite loops under weird cases? And who thinks it can't? Okay, so the people who took my class last semester know the right answer, that it can't. One of the magical things about this is that it cannot get in infinite loops. And the reason to see that is that every step A and B, for both A and B, cost 2 always decreases. It can, or stays the same. It can cost, this two-dimensional cost function can never increase. And that means I can't get to a previous state, because that would have had the cost of a state is well defined. Right? For a given set of centers and an assignment, right, I can define a cost, and that never increases. Okay? That's easy to see in the first step, because I'm always assigning each point to a center that's close, the same or closer than the previous center. Right? So given a fixed set of centers that I derive from B, right, it's either from whatever, if I use the same index of the center, right, as defined in B, I could keep that center, or I can reduce it to a center which is closer. The closer center will always have the smaller cost. Okay? And then step B, this is now the real magical part, in that given a set Si, right? So if I'm given a set like SI, a set of points which are all closest to some center, so CI, right, and there's some Voronoi diagram around here, right? The point, if I reassign CI, the point that minimizes cost 2, the sum of the squared errors, is the mean. Okay, the mean of any points in RD under the Euclidean distance is the sum of the squared. The point that minimizes the sum of the squared distance is exactly the average. Okay, and so this gives me a way to reassign the center, and with respect to the points mapped to it, it's always the optimal choice of center. Right, so both of these steps are decreasing the cost function, so the cost is always decreasing. So it can't get into infinite loops. Now what people have shown is there are weird cases where you may take an exponential number of steps. These are like crazy examples that don't really come up in practice. But you could take an exponential number of steps before it stops converging, before it stops making progress. But that's kind of rare. There are two things, and it's not guaranteed to find the global optimum. It could be that it gets stuck in some local minimum. Right? It could be that my data set looks like this. Okay, and my set of centers, this is going to be C1, this is going to be C2, and this is going to be C3, right? K is 3, there are 3 clusters, but if I stop here, what's going to happen is that these are going to divide here, and then I'm going to get some divisions like this, and so after one step, I'm going to move C1 here, C2 is going to be the same, and C3 will be the same, and then it's just going to look like this, and it's going to stop. Okay, this is a local minimum. It will not improve from here, but this is not the best answer. The best answer, of course, looks like, right, where it looks like this, where I have 3 points, one in each of the clusters, where here I get 2 points stuck in this cluster and 1 point stuck up there, and it can't get out. So it's not guaranteed to find the right solution. There can also be weird cases where one of the data points is assigned 0 points. There are no points that are closest. They're one center. There are no points closest to that center. And there's a few weird things that can still happen. Some corner cases. If this happens, if this happens, then the common thing to do is do a random restart. Okay, that means I'm going to randomly redo step 1. I'm going to randomly reassign the starting centers, and then I'm going to run it again. And usually, if a few random restarts, one of them will not get in this bad configuration. And you can tell because the cost will be lower. You can just look at the cost. That you do 5 random restarts on the algorithm, and the one with the lowest cost is the one that you pick. Okay, so it can get stuck in these local minimum of cost too. So it's not guaranteed to converge to the optimal answer, but it's guaranteed to converge to some answer. Okay. Okay, but there's one more point I want to come back here to, and that is how do I choose these case centers to start with? Right, I said arbitrarily here, but it turns out we can do something a little bit smarter than just choosing them arbitrarily. Right? How to choose the initial centers. How should I choose the initial centers? Yeah.
You can use the case center algorithm.
Great. Great. So the first idea is run the case center the, say, the Gonzales algorithm. So I run Gonzales algorithm, and this generally does pretty well, right? This will give me centers that are pretty well spread out. In particular, on this example, it will guarantee to do the right thing. I can't get a 2 approximation if I have the centers structurally wrong, right? So at least for the case center formulation, there are different approximations, but you could check on that example. You can't go wrong with Gonzales algorithm. It doesn't always work because it's optimizing the wrong value function node. I could have a situation where I have, let's say, 1 million points here, 1 million points here, I would have 1 point here, and this is very far. Okay, and I want 2 clusters. Gonzales will give me 1 cluster here and 1 cluster here. Where with Lloyd's algorithm, and maybe for the case center algorithm, that's the right solution if I have an outlier. It turns out that's what minimizes the cost. But with the case center, with the Kmeans algorithm, I'd rather have C1 and C2, and then charge the outlier because I have 1 million points here. I'd rather do really well on these points here. And so for things with outliers, case center does not always work as well as you'd hoped. I can also do something like randomly splitting the points up into different things and choosing centers. Another thing that works okay is to choose k log k centers. And then, and I choose these somewhat randomly or using Gonzales algorithm, and then by and this is maybe O of k log k. And then by coupon collectors, I'm kind of guaranteed to hit any large enough set. It's hard to prove something too formally about this, but in general, you can choose more centers, and then once you have them, once you've done the clustering, then I can merge stuff back together. Then cluster, then merge. Okay, so this is also not so bad a solution, and certain large-scale versions will do something like this. There's some good rationale for doing this. But what is generally kind of considered the right thing to do is a pre-processing algorithm called Kmeans++. Okay, and I have 5 minutes to tell you what Kmeans++ is. Turns out it's very simple. And Kmeans++ has some guarantees, like if you restart it some 8 times, then with high probability, it will do some approximation of the optimal solution. There are some formal guarantees. In practice, it works much better than what people have proved about it. Okay, so it's going to look a lot like the Gonzales algorithm. And so it's confusing is this, it says Kmeans, but this time it's an algorithm. Like Kmeans and case center are formulations. This is the actual name of the algorithm. Sometimes this is called D squared sampling as another name for the algorithm. Okay, but it's going to look like the Gonzales algorithm in that I'm going to start by choosing C1 out of X, the center C1 arbitrarily. Okay, so this step again can be arbitrary. And in general, I'm going to have these definitions again of a set. Ci is going to be the center C1, C2, up to Ci. Right? So I'm going to maintain these sets of centers. I'm going to grow it iteratively. So this is going to be a nice simple algorithm like that. And then 2 for I equals 2 to k. Then I'm going to do the following step, and this is a bit trickier. I'm going to choose Ci from X with proportionally are proportional to I'll write this in general, the distance from x to the set Ci of x squared. All right, so I'm going to calculate the score of every point. I'm going to square it because we're doing k-means. It turns out if you want to do k-median or k-medioid, you want to not square it, and then this is kind of the right thing to do. But in this case, I'm going to look at the cost of every point, square it, and I'm going to pick it randomly proportional to this score. Right? So what I would do is I would let W equals, I'm going to say this is the weight of x, is the sum over x of the sum of all these weights, and then I'm going to assign a probability to x, which is Wx divided by uppercase W, right? So now this is the probability I want to pick the point x, right? For points that are already centers, this is 0 because this distance is 0, right? And if they're far away, this is going to be large. Okay, so if there are a lot of points far away, in some cluster that's very far away from the centers I picked, they're all going to have a large score, and there are a lot of them. If there's one outlier far away, well, it has a large score, but there aren't a lot of them, right? So it might not get picked. I need to choose points with this probability. There's a faster way of doing that, but let me just say, how would you do this? But then once I have these probabilities, I'm going to go from 0 to 1, and I can think of putting them in here. This will be P1. Maybe this is from 0 up to 0.09. And then P2 will get this spot in here up to 0.18. And P3 occupies some space up to 0.23 and so forth. And then I'm going to choose a random number. So I'll think of mapping all of the data onto this line between 0 and 1, and then I pick a random number, and let's say it's 0.21, and it falls in this bin associated with P3. So I pick P3 as the next. So I pick x, the third point x, as the next center. Right? And so if it has a larger probability, it has a larger chunk, a higher chance of getting hit. Okay, and so this is the Kmeans ++ algorithm. Again, fairly simple. I need to implement this pick proportional to probability step. It's not too hard to do, right? I can calculate the probability this way and then use one random number, uniform random number between 0 and 1 in order to select the probability. And you can build a binary tree on this and then do binary search to find out. I don't need to scan through them. But I don't have time to explain. Okay, so this is really the best, kind of considered the best way to seed K-means, and it's built into a lot of libraries now, just like Lloyd's algorithm is built into a lot of libraries. Okay, if you want to see more about mixture of Gaussians, I've got more details on that in the notes. It's a way of doing soft clustering, and you not only fit centers, but you also fit a variance on top of the clusters, and you kind of assign a point based on which Gaussian describing a cluster best has the highest probability of representing that.